Academy, and we are looking at closure theorem. Closure theorem is one of the key theorems that we have in real analysis. Before we proceed, first thing first, kindly subscribe to this channel, share also with your friends. Okay, closure theorem. Closure theorem comes in two parts, about union and intersection. So part A of closure theorem is the union of any finite number of a closed set is closed. So if you get a finite number of closed sets, you find they are closed, the union. Then the intersection of an arbitrary number of is closed set is closed. The intersection of an arbitrary number of closed sets is closed. So those are two. So let's prove the two parts of the theorem. Proof from the union. We let a given union defined in this form S to be a given union defined with that. So where each I are closed, because we are talking about union of a finite number of closed sets. So these are closed sets S, A, I's, so they are closed. So if you get the complement of these, which we know it should be opened by the last principle. There is the last theorem we looked at about it says that a set S is closed if and only if its complement is open. That is a principle that theorem we have just in the previous tutorial about isolated points. You can check it up there. Look at how we proved that. So you find that by De Morgan's law, the complement of that, yes, it will follow that same extension for that complement. So that since i's are closed for our highs, then it will mean the i's complement are open for our highs. And since the intersection is also open, it will mean that the complement of S is open by that relationship, and SS is closed. And that now gives us a conclusion of that. Even the unions of their highs are also closed. So you have to link that. And that the ends of the proof, and simple as that and clear as that. Now B, let for intersection, now we let S to be that intersection for highs from high to n, where each eyes are closed, or eyes are closed, so that if you get the complement of this, you find that this is true, and by De Morgan's law, that is also true. Union and the complement are true by De Morgan's theorem. So that because in this case here, you find i's are closed for I highs, and it will mean that because i's are closed, it will mean that if their complement are open for highs, their complements are closed open for highs, and that since their union is open, it will imply that because now we are in this, it's open, it will now imply that even the S complement is open, and therefore it will mean that if S complement is open, then S is closed, and by that you find that its intersection are also closed, and therefore the intersection of four arbitrary numbers of closed sets is closed, and that marks the end of the proof. So kindly I have to leave you with this remark, which is a bonus for this. So the union of arbitrary family is closed, of closed sets need not to be closed set. So don't say that every time that we have a closed arbitrary family of closed sets that they will be obvious, the union will be obvious be a closed set. For example, if you consider this family here for intervals, for i's and they are closed, where higher is now is defined by this, you'll find that if you look at this clearly, you'll find that and every I here is a member of natural set. So being a closed interval, you find this a closed set. This is a closed set, of course. And now if you take now its unions, if union of i's, you'll find that this ranges from -1 and 1. Okay. The union will range from there, and that's open. This is an open interval. An open interval is an open set. We know that. So you see that I've gone opposite to our expectations. That means true. So it opens sometimes as per that remark. So for now, kindly subscribe and share with your friends, and I'll keep posting this kind of pure mathematics, real analysis, very interesting part of mathematics. Okay, bye for now.